start recording. Okay, good. And someone just came on. Okay, so um, let us start section 12.5. Equations of lines and planes. So before I tell you about equations of lines and planes uh, in general, and let's recall equations of lines that you had from your previous courses, like in elementary algebra, intermediate algebra, pre-calculus, etc. So first, the slope-intercept form for the equation of a line, y equal mx plus b. I can write this in a different order. So let's write this as y equaling, one second, y equaling b plus xm. So we can think of this as really being the equation of a line through the point 0b in the direction of the vector 1m, meaning you go in the direction where if you move 1 in the positive x direction, you move m in the y direction, the slope. So let me give you some equations of lines for vectors. So first, the vector equation through r0 in the direction of v. Well, it's r, the vector r, equals the vector r sub 0 plus tv, the t times the vector v, which is an equation exactly of the same form that I had from before. Let's recall the parametric form for the equation of a line, x equaling x0 at, y equaling y0 bt. Well, actually, if I do this for a line in 3 dimensions, it's the same thing. So the parametric equation through the point, through the initial vector, x0, y0, z0, in the direction of ABC is, is x equaling x0 plus at, y equaling y sub 0 plus bt, z equaling z sub 0 plus ct. So it has the exact same form. Let's recall the symmetric form for the equation of a line. If you don't recall how to do that, suppose I just write down the point slope form for the equation of a line and replace m here by b over a. Then if I divide both sides of my equation by b, I get the symmetric form for the equation of a line, y minus y0 over b equaling x minus x0 over a. Recall that this form for the equation of a line can be written even when the case that either a or b is 0, under the understanding that if, let's say, a is 0, then this means that the numerator must also be 0, that x must equal x sub 0 for all x. And so under that assumption, then I can write any line in this form. Okay, well, analogously, we have the symmetric equation through the initial vector x0, y0, z0 in the direction of ABC. Is just x minus x0 over a equaling y minus y0 over b equaling z minus z0 over c. When I write two equal signs like this, what that means is that any pair that you pick are going to be equal. So this x minus x naught over a is equal to y minus y naught over b, and x minus x naught over a equals z minus z naught over c, and y minus y naught over b is equal to z minus z naught over a. So any of those sort of combinations. And again, it's under the assumption that if I divide by 0, then the numerator must also be 0. The 2-point form for the equation of a line. So if you recall, the 2-point form for the equation of a line is just y minus y0 divided by x minus x0 equaling y1 minus y0 over x1 minus x0. I can rewrite that, just basically multiply by x0, y0, x1 minus x0 over, basically cross multiply. And then, so bring this guy over here and this guy over there. So if you do that, then you just get x minus x0 over x1 minus x0 equaling y minus y0 over y1 minus y0. Okay. And so, analogously, we have the 2-point form for the equation of a line. And so suppose you have some point x0, y0, z0, another point x1, y1, z1. Then you can write the equation of a line in the form x minus x0 over x1 minus x0 equaling y minus y0 over y1 minus y0 equaling z minus z0 over z1 minus z0. And again, this means that pairwise they're equal. Next, let's recall the parametric form for the equation of a line. And so I have here y is equal to t 1 minus t times y0 equaling t times x0. And so, analogously, we have the parametric equation from the vector r0 to the vector r1. We can write that as, well, r, the vector r, as a function of t is just equal to 1 minus t times the vector r sub 0 plus t times the vector r sub 1. Recall the standard form for the equation of a line. And so if I go through a point x0, y0, then these are equal because they're both equal to c. So subtract, bring these to the other side of my equation. And so this is equal to 0. And so I can think of this as just being a dot product. Oh, well, I'm sorry. Actually, I should maybe have written this way. One second. And so I can write this as this dot product. And if I bring these to the other side of my equation, I can think of this also as write it as a dot product. Okay, so let me do the vector equations of the plane through the vector r0 and having a normal of n, the vector n. So this is just equal to, well, the vector n time dot r minus the vector r minus the vector r sub 0, which can be thought of as this. So that's the same as this equation. Or the vector n dot the vector r equals the vector n dot the vector r sub 0, which is really this equation. And lastly, the scalar equation of the plane through the points x0, y0, z0, and a normal, a vector, a, b, c. Well, this is very similar to, well, if I would have written, I didn't write, ax plus by plus is equal to 0. So, this is right here. That's this guy here. So this equation is analogous to the scalar equation of the plane through x0, y0, z0 with normal ABC. So it's just a times x minus x0 plus b times y minus y0 plus c times z minus z0 equaling 0. So that's this equation here that you knew from before. The linear equation in x, y, z, ax plus by plus zz plus d equaling 0. That is the analogous equation to the standard form for the equation of a line. So note, analogously, when we had the distance from a point in the plane to a line, we had the distance equaling something looking almost identical to this. So the distance from the point x of the vector, let's say the vector x1 z1 x1 y1 z1 to the plane ax plus by plus cz plus d equaling 0 is given by, well, a x1 plus b y1 plus c z1 plus d in absolute value divided by the square root of a squared plus b squared plus c squared. So this is identical to what we had from before. The only difference is that this is has three. So this is in 3D rather than in 2D. So let's do some examples. On page 871, in exercises 2 through 5, find a vector equation and a parametric equations, and the parametric equations for the line. Okay, so let's do that. So the line through, so problem number 4, the line through the point 0, 14, negative 10, and parallel to the line x equaling negative 1 plus 2t, y equaling 6 minus 3t, z equaling 3 plus 9t. So it says to find the vector equation. So my vector equation was r, vector r, equaling vector r sub 0 plus t times the vector v. And so I have that r, the vector r, is equal to, well, let's do the initial vector. And so the initial vector will have coordinates 0, 14, negative 10, plus t times, well, the direction vector. So the direction vector, well, it's through this line, and so parallel to this line, so it has the same direction as this line. So let's find the direction of this line. So the direction of this line is, well, 2, negative 3, positive 9. And that is the vector equation through the point, through the vector, the initial vector, 0, 14, negative 10, in the direction 2, negative 3, 9. So let's find the parametric equation, or parametric equations. Okay, so let me just write them, I guess maybe all on one line. So x is equal to, well, we start at 0, and we have a direction of 2. We start at 14, and we have a direction of negative 3. We start at negative 10, and I have a direction of 9. And those are my parametric equations for this line. So, in exercises 6 through 12, find the parametric equations and the symmetric equations for the line. So let's do problem number 10. The line through the point 2, 1, 0 and perpendicular to both of these vectors, I plus j and j plus k. So to find a direction, a vector, perpendicular to these, well, I want to, find a, I can take a cross product. If I take the cross product of these two, I'll get a vector perpendicular to these two vectors. And so, let's call it vector W, which is just, maybe I'll call this U. No, so let's say I plus j. I want to cross that with j plus k. So this will just be the vector. That's I, j, k. And so I get 1, 1, 0, and I get 0, 1, 1. So this is going to equal, so if I think here, 1, 2, 3. So I do 1 first, so it's 2, 3. So 1 minus 0. And then it is 3, 1. So 3, 1. So 0 minus 1. And then it is 1, 2. 1 minus 0. And so I get the vector 1, negative 1, 1. So I get I minus j plus k. Okay, so that is a vector perpendicular in a direction perpendicular to these two original vectors. So let's do the parametric equations. And so the parametric equations are x equaling x naught plus at, y equaling y naught plus bt, z equaling z naught plus ct. And so this was through the point 210. Okay, so let's do this. So it's through the point 2, and this was I, 1, and this is minus j, 0, and this was k. And that, and those are our parametric equations. Let's do the symmetric equations. So the symmetric equations. So the symmetric equations are x minus x sub 0 over a equaling y minus y sub 0 over b is equal to z minus z sub 0 over c. Oops. 1 second. So let's do x minus x 0 over a. Okay, so I have, you can think of this as just solve for t. And so I have x minus 2 over 1 is equal to y minus 1 over negative 1 is equal to z minus 0 over 1. And those are our symmetric equations for this line. In exercises 23 through 40, find an equation of the plane. Problem number 24. The plane through the point 5, 3, 5 with the normal vector. Yeah, let me see if I can. There. That looks a little bit better. With the normal vector, 2i plus j minus k. So let's do the equation of plane. And so we'll do a x minus x sub 0 plus b y minus y sub 0 plus c z minus z sub 0 is equal to 0. Let's use this form because, well, we have a point and we have a normal vector. And so we can directly do this. So this will just be, well, note that the plane of, and so this is just going to be 2 x minus 5 plus 1 y minus 3 plus minus 1 z minus 5 equaling 0. So that is the equation of my plane. So it's not so crowded. Okay, good. So let me do the following. So I have that in exercises 45 through 47, find the point at which the line intersects the given plane. Oh, so I just want to figure out when when this line intersects, wait, three x minus y plus 2z equaling 5. Okay, so let's figure out that. And so, I have that 3t minus 1 plus, minus 1 minus 2t plus 2, 3 minus t is equal to 5. Just replacing x by t minus 1, y by 1 plus 2t, and z by 3 minus t. So let's simplify this. So I get 3t minus 3 minus 1 minus 2t plus 6 minus 2t is equal to 5. Let me combine like terms. So I get 6 minus 4 is 2. 3t minus 2t minus 2t is a negative 1t is 5. And so t is equal to negative 3. And so let's plug it in. So I have 3 equals negative, t equal negative 3, so x is equal to a negative 3 minus 1 is a negative 4. Y is equal to 1 minus 6 is a negative 5. And z is equal to 3 minus a negative 3, 6. And so the point of intersection is the point negative 4, negative 5, positive 6. And that's my point of intersection. Oh, and that's it. So I guess that's it for today. Let me stop this.